I will sit here and wait for you. Happy Sunday afternoon. Sorry for the nails on the floor. I have a Twinkie with me. What you looking for, Twink? Hello. What's up, buddy? With a Russian accent. That couldn't be more random, Dennis. Well, ask me if y'all have questions or anything. Preferably about science. I don't know the meaning of life. Lauren, Zelly, and Stacy. Hello! Zelly, I emailed you back. Hopefully you got that. Zelly sent a question earlier that is actually probably useful for a lot of people when you're thinking about things like aldol reactions and Michael reactions, where if you are looking at a reaction of some sort, you know, like what's a good way to keep track of what you're doing? And oh goodness gracious, what have I done? I started thinking aldol and then I drew a, that doesn't work. But basically, how do you go through something like this and figure out what carbons are going where and things like that? I did use color coding on the board for a reason. I think it's easier to help see what's going on if you can color code one molecule and then the other. But never underestimate how useful numbering things can be. You know, you can number one molecule with numbers and the other with Greek letters if you're Matthew, or just letters if you're other people, or you know, however you want to do it. You can even keep using numbers and just kind of go one through whatever, and that can really help make sure that you're, excuse Twinkie, he's warping, but that can kind of help you see what, you know, which atoms you've already taken care of. You shouldn't be losing carbons in a reaction like the ones that we've been looking at. Right, so if you look at your product and it doesn't have the same number of carbons as what you started with, that can be an issue. Oh, an amide from an acid chloride was it you need? You basically just need whatever nucleophile you need to replace the chloride. And that goes for all those carboxylic acid derivatives. So let's say you want, let me do this one. The desired product would be something like this. Sorry, I know it takes a minute for me to draw everything. And so you're looking at your amide there. What would I have to use to displace? collagen. I'm trying to find there we go. There is an actual retrosynthesis arrow here. But you would basically need aniline for this reaction, right? And the acid chlorides and the anhydrides are both so reactive that you don't really need anything else to do it. You don't need a catalyst to speed things up or anything like that. You just do it. I know I don't spend a lot of time with you guys focusing on the different solvents that we need for things. But you know, there would be solvents involved. I think that's hopefully obvious. But yeah, you would end up with some sort of reaction like this. Does that make sense, Dennis? And for those of you who are looking and not commenting on anything, if you haven't seen this kind of double-sided arrow, it's not a double-sided arrow, but an arrow that looks like a equal sign kind of in the middle. That's what we used for retrosynthesis, meaning synthesizing things backwards, like working backwards from your product to your starting material. And Dennis, that question that you asked applies to basically all of the carboxylic acid derivatives. You know, if you were looking to make an ester, you'd use whatever alcohol you need. If you were looking to form an anhydride, you'd use whatever carboxylate group you would need. So those are pretty straightforward. I know I just spent one day on them. So not a ton of time, but they're all really, really similar. So once you get the first couple down, you should be good. Next question. YouTube tells me there's 10 of you guys watching me, so I'm hoping some people have questions. If you don't have an outright question, could you say something like, could you give me an example of blank? That would also be useful for me. I guess Stacy hasn't. Stacy, we emailed you a couple times this weekend to get Miller notes. I guess you haven't seen us. He wasn't in class on Friday. Miller, I think your absences this semester is reminding us all how happy we are that we don't have a bad back. That's okay. Yes, he does still need them. Thank you, dear. I told him what to cover, but I guess, you know, having like professor notes kind of feels like having a safety blanket. You know, like you can definitely read this stuff online and in your book and stuff, but sometimes it's different when you see it in my handwriting or something. I don't know why. I never felt that way about professor PowerPoints, though. I was just like, I can look those up myself. But like their handwriting, suddenly it turned into something I needed to have copies of. I hope everybody's hydrated right now. I'm drinking green tea with honeysuckle in it. It's quite tasty. Zelly asked a question earlier on a naming question. Stacy does take amazing notes, but she also has the copies of my notes, so that she sends to Janae if Janae wasn't in, and Janae wasn't in, which means Stacy has my notes and her notes. Stacy has all of the notes. Anyway, Zelly asked me a question on email earlier, and it's one that is a good question and kind of one of those little nomenclature, like, I don't want to call it an exception, but, you know, like sometimes things become ambiguous, and like the molecule I have here, how would you know how to number it? Right? We have ethyl and a methyl group, and they both are the same priority. You know, they're both alkyl substituents on another aromatic, or not aromatic, alkane. So how would you go about knowing how to number this, especially if it's in a ring, right? Because I could number it 1, 2, 3 or 1, 2, 3, and it wouldn't change the numbering. Okay, so if you'll notice, if you number this, or name, whoops, if you name this, it's going to name the ethyl group as number 1 and the methyl group as number 3. It would number a propyl group number 3 compared to an ethyl as well. That's not because ethane is just amazingly more reactive than these or anything. It's just when it's ambiguous, it goes by alphabetical order. It's the same way with the halogens. So if I had, let's do a bromine here, and a chlorine. Oh, shoot. I just suddenly realized I have too many. There we go. So if you name something like this, it's going to name the bromine first, just because of alphabetization. I mean, that's it. I cover that very briefly in Organic 1, but I would never hold you guys responsible for knowing really weird little tiny rules like that, if you'd have numbered that either way. I try not to give you guys stuff that would be ambiguous like that, but sometimes I accidentally do, and then I just count whichever way you did it, as long as it makes sense. In the aldol reaction, which carbon in the enolate attacks the carbon from the aldehyde? Good question. Okay, so let's kind of draw an intermediate looking thing here for an enolate. Oh, there we go. To do this and have so many screens up, I have all my screens are shrunk, so a lot of my toolbars, you know, disappear when I shrink my screens and only take up half my desktop. So if you guys see me looking for a lot of stuff and I look confused, that's the reason why. Okay, so that would be I'm doing real easy here. So we have an enolate. So an aldehyde, a ketone that's already reacted in an aldol reaction. So it's already been deprotonated. So what I want you to think about is which carbon you're looking at here. And this could be a much longer chain of carbons, right? It doesn't matter. It doesn't have to just be a CH2 group. It could be a long chain of things. but it relies on the double bond being reformed between the carbon and the oxygen here, right? So if that bond is reformed here, oh, come on. Obviously that's going to make way too many bonds on that carbon. And so this bond comes out. So really you're looking at this CH group here. You're looking at the resonance structure, in other words, that has the negative charge on that carbon. There we go. So if you look at those as resonance structures, which they are, right, they're resonance structures of each other, only one of those is going to be able to react, only one of those carbons. You couldn't have the carbon attached to the oxygen doing any kind of nucleophilic work on this. Okay, so you're really looking at this molecule here, kind of at the bottom. I think you guys can see my cursor. Hopefully you can see my cursor because I'm circling things with it. And then if you need to, let's see, draw arrows. Sorry, just give me a second. There we go. So if I have So when you attack there, hopefully that kind of shows you what you need to do. And then this bond here would break and put the lone pair on the oxygen. So, Grace, I will answer your question here in a second. I want to see if you guys can figure out what the product of this aldol reaction is. Go ahead and show it as the, why am I having so many problems with arrows today? Here we go. So go ahead and show it with and without the dehydration step. So I'll go ahead and put it in here as two separate steps. Didn't copy it with like a lot of really good detail here, but I think it's good enough for what we need to do. So what I wanted to do is just kind of show you, do some colors here. So I've got carbon 1, 2, 3, 4, 5, and then I'm just going to go down here or over here and number that one 6. Okay. So I basically just went around and then did number 6. And it doesn't matter what order you do that in at all. It's just kind of however you want to do it. Well, I know that carbon 1 didn't have anything happen to it, so I'm just going to put that bond there. Like my skeleton is going to be the same for the first molecule on the left. I didn't change anything there. I didn't, you know, cut off an oxygen or break off a carbon or anything. What I did do, though, is reform a bond between the oxygen and carbon. And then on that alpha carbon, I attached to this guy over here. So carbon with 2 hydrogens on it. and an O. Okay, that's going to get get protonated. I'm not going to show that step, but you would end up basically getting that molecule. Okay, so the next step then is the dehydration that happens if there's any kind of heat, and by heat I mean literally like room temperature will do this. But I think it's good for us to kind of separate them that way. And then you get the dehydration product. So if you notice though, there's different ways you can draw this to give you stuff. You can draw everything in a very linear form. You can draw things kind of curved. You can draw things however you want that's going to help you kind of see what's going on. For me, personally, I like to be able to line this up with this, right? I like to be able to see those two kind of next to each other. That helps my brain see it better. But to each their own. Some of you may or may not be able to do that. It's just kind of how your brain works on figuring them out. So then the next question was from Grace, how to do some acid chloride nomenclature. So I'm going to pull us back to ChemSketch for that. Okay. Since ChemSketch will do all my naming for me. So all you have to do is remember that, and this is pretty much for all of the acid, or all of the carboxylic acid derivatives. Okay. Name everything first in your head like it's a carboxylic acid, and then go through and change the oic acid to oil chloride or to O8 or, whatever, amide, whatever it is that you need to do. So if this was the carboxylic acid, we would just call it benzoic acid, right? And so because it's the acid chloride, we would just change the oic acid to oil chloride, and so we would have benzoyl chloride. Okay. If I had that as the amine, the amide, we would end up with benzamide. Instead of oic acid, you just change that. If I have a nice long chain of carbons, let's do 7, and then on the end there I have an acid chloride. If you notice all the carboxylic acid derivatives, we didn't number anything on those because they're by definition going to be at the end, just like a carboxylic acid or an aldehyde, so you don't need to number them. But so here I have this acid chloride. Let's put something on it like a methyl. Okay. So here you would have 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5. So 5-methyl heptanoyl chloride. Should be the name for that. Yeah. Again, if it was the acid, you would have just done 5-methyl heptanoic acid. So you're just kind of changing the suffix there, but it's not going to be drastically different from the other naming you've done. In the Michael addition reaction in class, you said it could happen in any ketone. Basic double bonded O ketone. Yes, you need to have 2 of them to do the one that I showed you. So you have to be able to deprotonate the alpha carbon. In the aldol reaction, you saw us deprotonating an alpha carbon. So that's totally a thing that, it says thanks in all caps. Totally lost my train of thought, I'm sorry. But yes, so the one that I showed you, and I mentioned that there's Michael additions and there's Michael-like additions. There's actually a whole class of reactions that could take up an entire semester of our class that are very similar to the Michael addition I showed in class. The reason I showed it with the 1,3-dicarbonyl is to kind of push you guys to see the acidity of that kind of in-between carbon and how that's a little bit different than the other alkane carbons that we've seen before. And so that was kind of the classical Michael addition reaction. And so you could do it though with esters, diesters. You could do it with a bunch of different things as long as there's 2 carbonyls there. Or you can actually do it with 1 carbonyl also, but I didn't give you any examples of that. And I wasn't expecting you guys to do anything other than the one that I showed you the other day. Let me know if that makes sense. I'm going to drink some tea. Fantastic. If I have any other fellow popcorn lovers, I don't know if you've ever been to the Kroger's here in town, but they have these enormous bags of popcorn, and it tastes like movie theater popcorn. It's really good. Highly recommend. You can get a huge tub of it. This big bag's like $4 or $5, I think. Purpose, what is the purpose of a Wittig reaction? Who knows? No, it's so you can basically, it's another way of forming carbon-carbon bonds, and that's always really important to be able to do. You know, if you think about all the stuff that we've done, like it's good to be able to change functional groups, right? Like say you needed an alcohol instead of an aldehyde, and you know can do that kind of reduction reaction or vice versa. But then there's also things like you might need to make molecules larger. And so being able to create carbon-carbon bonds is really important. And so a Wittig reaction is going to take something like a ketone or an aldehyde, and it's going to be able to convert that to an alkene with some other carbon that you use to make the Wittig reagent or the ylide. So that's kind of the purpose of a Wittig reaction. I hope that answers your question. But it's really useful to making longer carbon and bigger carbon molecules. We've really only seen a handful of examples over the past 2 semesters of carbon-carbon bond formation. So we saw the Wittig reaction, the Michael addition, and the aldol reaction that we did, obviously. The Grignard reaction. I showed how you could use a terminal alkyne and do like a nucleophilic substitution reaction on something to make a carbon-carbon bond on that. But that's kind of it. You know, it's when I talked to you guys the other day about how many reactions have we seen with alcohols. I mentioned this when we were doing our lab presentation, so if you're not in lab you wouldn't have heard this, but you know, think of how many reactions we've done where we've looked at alcohols, and think of how many reactions we've done looking at amines, but then how many have we done where we were adding carbon bonds and things like that? It's really not nearly as many. They're harder to do. Carbon-carbon bonds are really strong, so they're hard to break and they're hard to make. So they're really hard to break. But yeah, having kind of a repertoire in your mind of those different reactions can be helpful. It is really dark in here. I don't know. I'm going to turn the light on. That makes me look like I'm glowing. That's really weird. Hopefully that's not too weird. Megan is now a glowing orb on your screen. A yellow glowing orb. It's very exciting. There's a Fisher projection with fructoketose. In theory, I didn't spend any time covering those this semester. I just told you you could because I know I'm teaching you guys all biochem next semester, so I figured I didn't need to. I know you were going to get it next semester. So you don't need to know how to do that, but it's a good thought problem to look at it and say, yes, I see where this is going. Cool, cool, cool. Cool, 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 cheerio. I will. The concert I'm going to tonight starts at 8. And so I probably won't be. We usually leave, even if it's an awesome concert and stuff. We'll usually still leave by 11 if it's going on, since Brandon has to be at work at like 7 in the morning. And it's down Nashville, so it's an hour drive back. So I'll be able to come online and answer a couple more questions if you guys, well, not online, but like I'll check my email, is what I'm saying. I'll check my email tonight when I get home, and on the way home in the car I can answer questions too. So if you don't have them right now because you're still formulating thoughts, I can answer a few more questions tonight. Do you want me to just randomly give you a problem? Fine. I'll just start with this one. Okay. What chemicals would you need to do to form this imine? What reaction would you do? What two starting materials would you use? I'm going to break out my retrosynthesis arrow again. Give me a second to think of that. I think I have it right outside the door. Come on. Monster dog. I know. My giant derpy dog. 7, 8. Badam. Badam, I don't know what that means. There you go. Questions, class? A common mistake that I see people making with imine chemistry is that they will forget to put whatever's attached to the nitrogen on the molecule, so they end up with just making an amine, or basically like the ammonia version over and over and over, because they don't take the whatever the R group is with it. Make sure you do that. Again, if you start off a molecule with more carbons than you end up with, generally speaking, you didn't do something right. With some sold stuff to have some review. I guess you mean old stuff. Okay. Stop it! You're going to kill the quilt! Stop! Fred. I knew I shouldn't have let him in here. I was trying to be nice. Alright, name that one. Oh, and some new stuff? Oh, gosh. You're so demanding. Okay. Is there like a water there? There we go. Okay, name that one. Hopefully you got something that looked like that. Ask me questions. Oh, I know I said I wouldn't go over priority of the carboxylic acid derivatives. So I'm sorry if this one was confusing. Dennis asked for new and old. But basically you can assume that they'll always have top priority on the molecule. And I wouldn't give you one that had more than one. Name this. It has a carboxylic acid and an acid chloride. It's actually pretty interesting if you do it. I don't know why I'm thinking of Bradley and Victor. For some reason you guys always have questions like this, but if you go and you make one with like an amide and an acid, it'll name the acid and then it'll name the amide like it's a oxo group and an amine. Ah. So let me know if that makes sense. Do you want me to do another one? I'll do another one. Tricky hobbits. You guys are being really quiet tonight. I mean, like, you never make any physical noise anyway, since you're texting, but it's kind of weird, guys. Should I be alarmed? Okay. Use orthometapair to name that one. Curious actually how this works in person. Do you guys just like have sheets of paper that you work on while we're doing this? I guess I assume that's what you did, but I never saw. I should be alarmed. Don't tell me that. You guys have always been doing so good this whole semester. Don't let me down. This one up here, there we go. That one should probably be pretty easy. It would be like naming a fluorobenzoic acid, right? But you have a benzamide instead. I keep dropping popcorn on the floor. I'll do the easy one first. At least the one that I'm thinking would be easy for you guys. Okay. I told you guys to do orthometapair though, so which one would that be? First answer gets my unconditional love. Thank you, Dennis. Yes, it's meta. So, this one down here is a little bit different. So, what's my highest priority functional group on that molecule? Hopefully everybody's looking at that and saying, the ketone, of course. So that would mean that we need to name the molecule wherever that ketone is as having priority. Yeah. So that would mean we would have a cyclohexanone, right? But with a phenyl group on it, because the benzene is just going to be named as a phenyl group since it doesn't have the highest priority group on it. So there you go. I'm actually surprised that it's telling us that they numbered that with the 1, since where else would it be? But I usually tell people, unless it's something that's always on a terminal end, go ahead and number it. Any questions? Okay. kind of don't know where to go with this because you guys are being kind of quiet. Here, I'll give you a hard one. There we go. How could I make this, and I'll just put 3 arrows there. I don't know how many it'll take off the top of my head, but how could I make that from cyclohexanol? The way I need you to look at that and think about it is, what am I doing? What am I adding? What am I getting rid of? So at some point we're getting rid of the alcohol, but the most important thing to notice on this is you're making a carbon-carbon bond, which means at some point you need to be doing some sort of reaction that will form carbon-carbon bonds. So you could do, like a Grignard reaction or a Wittig reaction. This would not be the type of carbon-carbon bond formation that you would use to do. Could you do it with that? I guess if you're really careful, you could probably use an aldol reaction, but I think you could probably figure out ways to do this with a Grignard reaction or a Wittig reaction. I would personally use a Wittig reaction, because if I have an alcohol, I can very easily form a ketone. And if you can form a ketone, you can do a Wittig reaction. While you guys are working on that, Miller sent me a question about, here we go. Miller sent me a question about a review guide for the ACS final. And what I told him, and I'll tell the rest of you, is that the way that I grade the final is I look at how many reactions we've covered. Like, I go through the exam and find the ones that I think you guys should be able to do. So let's say it's 40 out of 50. I only graded out of 40. If you got 42 right, then technically you'd get over 100%. Nobody ever has, but still. But so that way, you can not worry about having to learn a bunch of new reactions during finals week that we haven't seen before just because they're on the standardized final. Those scores don't get reported to anyone. I still let you guys, use model kits on them, like what you've always done. So yeah, I hope that's helpful information for you to have. So hopefully you've gotten some ideas on this one that I have here. I think for me, the most obvious one to start off with would be to form the ketone. So we could do a Wittig reaction. So we could do something like pyridinium chromochlorate. Yeah, oxidation. That would form the, there we go. That would form the oxidized form of cyclohexanol, which would be cyclohexanone, the ketone. And if we have that, then we could do the Wittig reaction, where you would use, oh, this is going to be hard to draw. Okay. I think I'll do it this way. pH is a shorthand for a phenyl group. So triphenylphosphine with a CHCH3. It is the reaction that has the zwitterion, where it's a positively charged phosphorus and a negatively charged carbon. Or there's the alternative form where there's a double bond between them and it's uncharged. But either way, you would get a reaction where the product would look like that. So wherever the double bond is to the oxygen, you would form a double bond to whatever that carbon is attached to the phosphorus. And then it would be a pretty simple hydrogenation reaction, and you could use your pick of hydrogenation reactions. Palladium on carbon with hydrogen gas would be the first one I would think of. And there you go. Oh, goodness gracious. This is just not my day, is it? There we go. I'll just make it ugly instead. There you go. So hopefully that one made some sense. Did anybody figure out how you could do it with a Grignard? What do you need to have to do a Grignard reaction? You need to have a carbonyl, right? So this kind of thing, this reaction would still be in play. The one on top. Then you could add your Grignard reagent, and that would form an alcohol. And then you could dehydrate it to get rid of the alcohol. And then you could hydrogenate it. So that's another option for you. Okay. Well, I'm kind of tired of trying to come up with questions for you guys since you don't have any. I'm going to ignore Zelly's advice and comment on that and say that I'm pretty sure it's a good sign that you kind of know what's going on. But I'm going to go ahead and hop off here, and let me know through email if you guys have any questions. I've been checking my phone. We've been chatting, and I have not seen any questions come through that weren't able to come on the chat. So hopefully we're in good shape. I feel like we're in good shape. You guys really seem to know what you were doing on the extra credit that I handed out. You seem to know what you were doing in class. Most of you, most of the time. So I'm feeling pretty confident. There's Red Dog on the camera, scratching his chest. If you want to see something really awkward, it's a gigantic dog scratching anything. And then Red Dog Camera. Hey, buddy. You want to say hi? Yes. And then I've got below me Twinkie, who can't jump up on the bed because his legs are 6 inches long. So, anyway, I will talk to you guys tomorrow, or if you have questions tonight, you can go ahead and email me. So, thanks for coming and reviewing with me for this organic chemistry exam tomorrow. I hope you all have a wonderful night. I will talk to you tomorrow.